Let me start from the Sergei Streltsov question, which was done 2 days ago. Sergei, you are hearing me?
Yes, I am. I'm here. Yeah, thanks a lot.
Okay. So the question was, is the origin of spin-Thorne spectrum of non-centrosymmetric metals due to the exchange or due to the spin-orbit interaction? Let's start from single particle Hamiltonian. So this is electron in periodic potential in crystal lattice, and besides of periodic potential, there is spin orbital term with gradient with same potential and times the momentum. So it's standard spin orbit coupling term. Now let us transform this Hamiltonian to the reciprocal space. So let's take just Bloch function like this. This is a spin part of this Bloch function. This is a periodic function. And take the matrix element like this. Of course, when we take matrix element from this part, we obtain just band energy of electron. But from this part, it's just first correction due to energy due to spin orbital coupling. It's obvious that when we take this matrix element, we obtain the expression like this. Here is scalar product of gamma k and sigma alpha beta. I cannot calculate this gamma k. Only people who make upper initial calculation can. But I know the symmetry properties of this gamma. First of all, this expression should be Hermitian. It means that gamma is real. Now, if we apply time inversion to this term, we obtain the k to minus k and sigma to minus sigma. So, but if we our system time inversion invariant, it should be equal again with the same expression. So it's possible then and only then when this gamma function is odd function of k. So it's possible only when the space parity is broken. What does it mean? It means the application of space parity inversion operator to the spectrum. We see this part is even function, this part is odd function. It means that total expression not inversionally invariant. So this is the answer to your question. So the origin of this spin orbital of this gamma for non-centrosymmetric metals, it's just a spin orbital coupling. Now, if we look on exchange interaction, it looks like as follows: the same periodic Hamiltonian, but there is another term looking like this. This is the exchange interaction of again electron to many atoms, and also this part can also there is a part spin orbital interaction here. For instance, magnetic dipole-dipole interaction can be written the same manner. So, but in this case, in general, there is no time inversion invariance. That's why in general gamma is not odd function, but maybe even. So now let's start the next talk. What are altermagnets? There is a specific class of magnetic materials with symmetry, including operation of time inversion only in combinations with rotations and reflections of crystal lattice, or without time inversion at all. Symmetry of these substances is independent of translations. of period of crystal lattice, as it is in usual antiferromagnet. But it contains only rotations and reflections, but not translations. The elementary cell contain even number of magnetic atoms in each crystal elementary cell. During my talk, I will speak about two atoms, magnetic atoms in elementary cell, and 4 atoms in elementary cell. Now, these materials can be dielectrics or metals. The dielectrics possessing such a type of symmetry can be antiferromagnets, weak ferromagnets, ferrimagnets, and ferromagnets. To each dielectric possessing such type of symmetry, one can find the corresponding metal possessing the same symmetry, but without so simple picture with some spins in some crystal points. But anyway, the symmetry of electron bands in such a material should correspond to the symmetry of corresponding dielectrics. So in magnetic material in general, there is a Hall effect. What does it mean? It means that there is off-diagonal conductivity. So the response of current to electric field has a off-diagonal conductivity tensor. So it means that this conductivity tensor antisymmetric. What is the reason for this? The reason for this is magnetic field itself, magnetic moment of magnetic material, also the skew scattering of electrons on impurities, or tight jumps during the scattering of electrons on impurities, and also there is an impure, absolutely pure crystal without any scattering. There is another mechanism due to so-called Berry curvature, which is symmetry property of electron bands itself. So my question is, let's consider all altermagnetic, which have a symmetry corresponding to symmetry antiferro, weak ferromagnet, ferrimagnet, or ferromagnet. And now to each type of this material, question, is there a spontaneous magnetization? Of course, for pure antiferric there is no. For weak ferro there is, for ferri there is, and for ferro of course. Now, this sigma off-diagonal sigma for antiferro absent, but weak ferro present, for ferri magnet present, and for ferro present of course. Now the question, is there a path corresponding to Berry curvature in this material exist or not? For I demonstrate that for antiferro it's always absent, for weak ferro present, for ferrimagnet sometimes present, sometimes absent, and for ferro sometimes present or sometimes absent. So you see there is difference between the general value of sigma ij and Berry part of it. Berry part may be absent, but this part always present. So a general rule that in general sigma off-diagonal sigma present in case of spontaneous magnetization. There are exceptions from this rule. For instance, in chromium 2O3, it's a so-called toroid antiferromagnet. In this case, magnetic moment absolutely absent, but off-diagonal sigma is present. But for this, there are special reason because it's a so-called magnetoelectric. But this one altermagnets. Now let's look on general situation. To look on general situation, it's instructive to recollect the known article by Igor Mikhailovich Zelashinsky, which was done more than half a century ago. He considered tetragonal antiferromagnet containing two magnetic atoms inside of elementary cell, this one and this one. So it's fluorides of transition metals like manganese, cobalt, ferrum, nickel. So here with black point I indicate magnetic atoms, and with circle fluor. So this crystal structure is tetragonal but non-symmetric. It means that the crystal symmetry, which is D for H, contains the operation of shifts on half a diagonal of elementary cell from here to here. So, for instance, it contains inversion, but you see at the same time as I told, but in paramagnetic state, this crystal has a symmetry like this times time inversion. So time inversion independent of all these operations. But below nail temperature, these atoms acquire magnetic moments, ordered magnetic moments, and now the group of symmetry looks like the same. So the same group of symmetry, but some of these elements, for instance, rotation on angle pi over 2 contains not only shift this atom to this place, but time inversion, because here the direction of these errors opposite. So Zelashinsky considered this from the point of view Landau theory, and he introduced two other parameters because two magnetic moments here, two magnetic atoms here, and he considered a linear combination of these magnetic moments, difference and sum of them, and decompose the Landau free energy in powers of these vectors. So, and found the different minima of this functional depending on the value of these coefficients here. So in real life exists only this combination, but in theory, depending on the different value of these parameters, one can find also another two possibility. One possibility, one L vector with the difference between magnetic moments parallel to X direction, and at the same time there is a small direction of spontaneous magnetization along Y direction. So this one, the group of symmetry of this is lower than this. It's due to H now. Again, there are a lot of elements which is combined with shift on half diagonal and with combined with time inversion, and looks like this. And we finally he found in our situation when magnetic moment along the diagonal of basal plane. And in this case, the symmetry of this crystal lower. So you see, this is tetragonal, this is orthorhombic, and this is a rhomboedral. And unlike too many other authors which now consider magnetic symmetry separately from the symmetry of a crystal itself, in real life it's impossible, and in real life it looks like as Zoloshinsky considered. So this rhomboid and rhomboidal crystal, and now it's symmetric. There is no such operation, because you see magnetic moment in this place and in this place are different. So so we see this is antiferromagnet, this is a weak ferromagnet because there is spontaneous magnetization, and this is a ferrimagnet. So the magnetic moment in different places are directed in the same direction, but they have opposite direction. Now let's imagine that we have metals with the same symmetry as all of these antiferromagnets, this, and this, and look on band structure symmetry for these materials. It's not so difficult to find that this again has such a structure. This is usual dispersion law with even function epsilon from k, and again the product of gamma k to sigma matrix, and with gamma for this case symmetric in respect of all of this operation looks like as follows. Symmetric in respect of these operations looks like as follows, and symmetric of all these operations looks like as follows. So you see this formally, this expression very similar to non-centrosymmetric situation, which I discussed in the previous part of my talk. Now let's look so on this analogy. Again, electronic states have such dispersion law. Space parity now present. There is inversion. So eigenvalues as usual like this. Fermi surfaces, two Fermi surfaces again like this. Two eigenfunctions. There is orthogonality between them. And also there is no Kramer's degeneracy, because the structure of this wave function is the same, and each of them corresponds to different energy. This one to this one to this. Sorry, this one to this one to this. Now, again, band splitting, again, quantization axis along the gamma vector. Again, the susceptibility looks like as follows as before. Again, there is anisotropy in presence of inhomogeneity. So it's quite similar to non-centrosymmetric metals. Now, the kinetic equation has this same form as before, and collision integral on impurities has the same form. One can solve it in so-called collisionless limit, in this limit, when the band splitting much larger than the rate of scattering of impurities in the same manner. And of course, one can discuss now magnetic moment as a response of these two electric field. So components of magnetic moment has the same form as non-centrosymmetric metals, and each of these correction to distribution function is the odd function proportional to electric field and odd function of momentum. So you see, but gamma x, gamma y, and gamma z now even functions. So all these integral now are equal to 0, unlike to non-centrosymmetric metals. So there is no magnetoelectric effect in this case. Now let's look on anomalous Hall effect. You remember that there was a term in expression for a current expressed through the so-called Berry curvature. And this integral in case of non-centrosymmetric metals was equal to 0 because gamma is odd function. Now let's look what is going on in case of altermagnets. In case of altermagnets, for antiferromagnet we have this value of gamma, and we can calculate this Berry curvature. And you see, this Berry curvature, odd function of kx and odd function of ky. So if we substitute this value to this integral, here it's just Fermi function, we obtain 0. So for antiferromagnet, sigma xy equal to 0. For a weak ferromagnet, you see there is a spontaneous momentum here, symmetric in respect to all operations. So calculation of this Berry curvature in xz component of this, we obtain completely even function of kx, kz, and ky. So substitution of this value to this expression, we demonstrate that in this case, sigma off-diagonal component of Hall coefficients is not equal to 0. For ferromagnet, it looks like as follows. The calculation shows that Berry curvature is equal to 0, and correspondingly there is no anomalous Hall effect. This property may be not general. It is particular case discussed by Zelazhinsky. Now, one can say several words about any altermagnet in the same time as a piezomagnet, because look, there is a piezomagnetic functional which is proportional to stress tensor component and component magnetic field. This functional invariant in respect to all the component, all the operations of this group of antiferromagnet. So differentiation of this functional, we obtain magnetic moment proportional to stress. In fact, this effect was measured by Borovik-Romanov many years ago. He applied to fluoride of I forgot, maybe to fluoride of nickel, tension along XY, and he obtained a magnetization of this crystal. So if there is a magnetization under stress, in this case, this gamma vector looks like as follows. So there is a shift in this Z component. Now, and calculations of Berry curvature looks like as follows. And then under the stress, we have off-diagonal component of conductivity. Now let's consider a more complicated case. It's a case of altermagnetic ferromagnet. It's a very famous material, uranium, germanium, rhodium, germanium. Why famous? Because it has Curie temperature. Curie temperature about 10 Kelvin at normal pressure. It's a pressure. at normal pressure, Curie temperature about 10 Kelvin. And we phase transition to a superconducting state inside of ferromagnetic state at temperature 1/4 of Kelvin. So it looks as situation looks like as follows: ferromagnetic state, superconducting state exists inside of strong ferromagnetic order. So the crystal structure looks like as follows. In fact, there was measured anomalous Hall effect in this uranium rhodium germanium. As in any material, magnetic material, resistivity of diagonal resistivity, that is Hall resistivity, is a ratio of electric field along y direction to current directed along x direction. It consists of 4 terms, in fact. This is a normal Hall effect proportional to external magnetic field. This is a part of due to Berry curvature, possible. And this part of due to side jumps, and this is a side due to skew scattering. The experimentator, this group in Grenoble, made about 10 years ago, they plot with dependence as follows. They divided both parts on h, so we obtain rho xy divided by h. There is rho 0, it's the usual Hall coefficient, and this one. And we plot this one as a function of this ratio m over h. So you see, one can measure, and they suppose that because of both of these proportional to to impurities, so this part should be proportional to usual resistivity. So they can measure resistivity independently. They can measure M magnetization independently and plot this field. So they obtain rho xy as a function of this ratio. It's a direct line. So in other words, there is no Berry curvature at all here. So because if such plot exists, such term exists, the dependence of this rho xy divided by h will be not direct line. So it was measured from room temperature to 12 Kelvin. It was done also in ferromagnetic state. So let's look why it's possible. This material, it's a non-symmetric crystal, and unlike to previous, it has 4 magnetic atoms in each elementary cell. So this uranium, 1, 2, 3, 4. So for non-symmetric materials with symmetry operations, so the positions of these atoms, 1, 2, 3, 4, looks like as follows. X has some value, Z has some value. This value is, of course, known due to the X-ray scattering. But the Y component is fixed. And it's fixed because it's a non-symmetric symmetry. So the group of symmetry looks like follows. So now there are not only a shift in diagonal like this, also shift in basal plane, not basal plane, but XZ plane like this. So, and this group consists of such elements. Here I enumerate all of them. And under this operation, each atom of uranium transform like this. Under, for instance, U2 under this operation transform to U1. And oops, under this operation to U4, and so on. Now let's look. So we know everything. We know the group of symmetry of this material, and according to our approach, one can find the band symmetry with gamma, and gamma corresponding to band symmetry of this looks like as follows. Again, we applying the same procedure. Calculating this conductivity expressed through Berry curvature, and calculation Berry curvature using this gamma, we obtain 0. So, and this corresponds to experiment. The Berry curvature in this material exactly due to non-symmetric symmetry of this material is equal to 0. Let's look now what is going on in symmetric case. So what does it mean? It means that it means let's forget that all the uranium atoms are in such positions. Let's shift them in some combination nearby the centrum of this elementary cell. In this case, the structure looks like as follows. Again, it's orthorhombic, but symmetry now is symmetric. No this element. So in this symmetric symmetry, gamma looks like as follows. If we calculate Berry curvature for this gamma, we obtain non-zero value of gamma, and even more. This is a so maybe I say several words about superconductivity. Because I omit this piezomagnetism in this material, it was measured because it's uranium, rhodium, germanium is piezomagnet. Also, and maybe only one single piezomagnet in between all ferromagnetic materials, because it's very soft ferro. Now about superconductivity. You remember what I did with BCS Hamiltonian in non-centrosymmetric material. I took this BCS Hamiltonian now without any triplet pairing. So and just transforming band representation. Apply this transformation. So you see, in non-centrosymmetric case, it was I obtained this combination, and you see here there is delta function lambda 1, lambda 2. It means lambda 1 equal to lambda 2. It means the pairing exists inside of each band. Pairing inside of band with lambda plus with lambda plus. Pairing with lambda minus to lambda minus. But if we calculate the same for altermagnets, we obtain instead of delta function here sigma x function. It means we pairing lambda plus with lambda minus here. So it's a pairing between the states in different bands, which is splitted by spin orbital coupling and also exchange coupling. So it's a situation quite similar to situation with usual superconductors and magnetic field, which create the FFLO state and so on. So here, without any magnetic field, we can obtain, inevitably obtain FFLO state. So let me just omit this complicated stuff, we've got equation and this stuff, and let us conclude shortly. A short summary. So altermagnets are magnetic metals with symmetry, including operations of time inversion only in combinations with rotations and reflections of a crystal lattice or without time inversion at all. They can be, their symmetry can correspond to corresponding antiferromagnets, weak ferromagnets, ferrimagnets, or ferromagnets. Number of atoms in elementary cell even. Anomalous Hall effect due to non-zero Berry curvature of electron band is realized only in altermagnets with spontaneous magnetization. So, and this table looks like as follows. So thank you for your attention.
Thank you for a nice talk. Please, questions. Are there any? Sergei Streltsov.
Yeah, Vladimir Petrovich, thanks a lot. So, typically, people consider altermagnets as those having the splitting in electronic bands, right, for different spin projections. So you consider it, you somehow use a little bit different definition as far as I understand. So you also consider ferromagnetic.
No, sorry, not different.
No. I mean that you. So let me come to this point exactly. So ferromagnetic altermagnet. So typically people speak about antiferromagnetic altermagnet, right? So
The people
like-
not know this stuff only.
So let me just maybe summarize a little bit. So in antiferromagnets, we typically have zero magnetization, right? And the total magnetization. And then altermagnetism gives us the splitting between different of electronic bands with different spin projection, but by symmetry operation, they sum to zero finally. Here you consider ferromagnetic altermagnet, which is something a little bit unusual. So we have to understand correctly that we have non-vanishing total magnetization in this uranium compound. Is this correct?
No. Let's start from the beginning. If you consider this stuff as altermagnet, there is no antiferromagnet. There is no total magnetization at all here. If you integrate and you see, this is a gamma. And if you calculate magnetic moment without external magnetic field with such a spectrum, you obtain zero. And again, as everybody consider with altermagnets, there is a splitting of electron bands and K dependent. So it's the same definition as
But I mean, for uranium, maybe I missed something. So you mentioned that
in uranium, this is not the case. In uranium, the gamma looks like as there is spontaneous magnetization in this case, and that's all. And
so do I understand it correctly that your definition in some way of altermagnetism is this combination that these are the materials where we must combine time reversal with rotations and
reflection.
Right? So this is your definition, as far as I understand, right?
Yes,
And these are not necessarily antiferromagnets.
yes, it's my definition a little bit more general.
Yeah,
but
exactly.
in,
This
in,
was exactly my
in,
question.
in case of antiferromagnet, it coincides with with usual.
Yeah, thank you so much.